Okay, so the history of PACE. We decided to include this for a couple of different reasons. Because, this is basically just a history lesson, not really a science lesson now. But the context we thought was going to be important because, for one, you need to have a sense of the time scale that missions operate on. I don't come up with an idea and then suddenly within a year I'm building it. In fact, if you look at the family tree here, you can see it starts in 2000. So basically, PACE has been a seed of thought for my entire career. I started in 1999. So it's a long, long time scale. The other useful thing about the history, too, is that you'll get a sense of the trials, the tribulations, the design struggles, and that's going to have context for when you meet the rest of the project and take the tour, because they'll be using language about like design trade space, what we did versus what we had to give up. And there's going to be a push and a pull all the time, no matter what kind of instrument you're developing here. So, figured that this is worth it because it'll make sense for why we are where we are today. And if you follow politics, you'll know PACE has been a troubled mission too, but we'll get to that. So anyway, like I said, the family tree starts around 2000. Basically at this point, at least it's starting really as an ocean mission, but it evolved into a multidisciplinary mission multiple times. But the conception was because CWIS was really successful. And when you know something's working and you're having a lot of success with it, you immediately go to the place of, well, what could I do better if I did it next time? And that's really where the origination of all this came from in this carbon program formulation. And so the idea, again, of this is we had some of these instruments, but there were so many other things that have since happened that weren't realized when PACE was conceived. And so this original top of the tree here was the project scientist for CWIS, Chuck McLean, the one who wrote the paper I told you about earlier, was approached by NASA headquarters, I can't remember the administrator at the time, to put together a recommendation for a full Earth carbon monitoring system. And it went to Office Management of Budget. It was a successful idea. They were going to get ready to go forward with it, and then September 11th happened. And they decided that was not how they were going to invest money. So just kind of an interesting, beginning of the whole process here. So there were a number of other studies in the middle part of that decade. Ultimately, it resulted in a 2007 advanced planning document put together by Ocean Biology and Biogeochemistry program at NASA headquarters. And there were you can kind of see where the evolution of the idea started going. Like, they always knew they wanted an ocean radiometer, but ideas about coupling it with a LiDAR started to emerge, or doing more terrestrial and atmospheric science. But I get the sense of there's a lot of studies that are going on. We're not cutting metal yet. These are just ideas to be proposed to the agency to kind of get them in the headspace of, are we going to invest $1 billion on something like this? And keep in mind, while the ocean and atmosphere community are doing this, heliophysics, astrophysics, planetary, all the other disciplines, all the other NASA centers, everything, they're all coming up with their own ideas. So it's a competitive market to get attention, which is why you go through these things. And then you had the 2007 Decadal Survey. And the outcome of that is in the slide from headquarters up top there. The important thing to realize there is that at Tier 2, it identified a number of missions that might start sounding a little bit more familiar. And they're precursors to some things that are going on today. So if you've heard of SBG coming out of NASA, that's just what Hesperi was then. Glimmer, the geostationary instrument I mentioned before, is a follow-on to the GeoCape type concept. But these decadal surveys are really where the community has a chance to influence what an agency like NASA will continue to do for their next decade. The important one for us is called ACE, Aerosol Cloud Ecosystem. The idea behind ACE was really where we were putting together oceans and atmospheres. There would be an ocean radiometer, but it would be capable to do some aerosol stuff as well. And anyway, you can read that little panel there. But the good news for all of us is because ACE was in the Decadal Survey, this kind of became a real idea now. PACE was starting to get some, it wasn't PACE at the time, but this mission, this observatory started to gain some traction, including a formation of an ACE science team that I think a number of people in the room, at least in the front row, were on. Well, ACE had its place, and we'll come back to it in a second, and documents were created that became kind of foundational for at least what the OCI instrument would become. But then in 2010, NASA put out a responding to climate change document that was supposed to be effectively a supplement to the 2007 Decadal Survey. And it was at this point they basically wanted a pre-ACE. So PACE is actually originally pre-ACE. The reason for doing this was the ACE concept, if I remember it correctly, was going to be 4 different instruments or 4 different technologies. There was going to be passive radiometry, LIDAR, cloud radar, and maybe polarimetry. But the general idea was 2 of the technologies were more mature than the other 2. So rather than wait for a 4-instrument observatory, let's get to the 2 ones that are ready out early. And that is where PACE became the first ones out of the gate. What happens next is you form a science definition team. That was in 2012. A lot of us were on it. It comes out with a 300-page document that effectively describes what the science of a mission like pre-ACE would be. And so what a science definition team typically does is that they come up with a series of science questions. They're usually grouped into threshold versus goal or advanced, but these science questions are what are supposed to define what the mission in the observatory is going to look like. And then you track your science questions into, and I'm sorry, what I was showing is that there were ocean science questions, and then there were also atmospheric science questions. And then those science questions eventually, let me do this in reverse. Okay. I put these in the wrong order. You identify the science questions because all of your instrumentation is supposed to be grounded in science. And then once you've done that, you start describing what kind of instrumentation would be required to build up the capabilities to answer those science questions. Never does work that way. You get back to the engineer saying, I've got an idea, what can we do with it? But I want you to see that effectively this document is where the idea of putting passive radiometry, like ocean color hyperspectral type radiometry paired with polarimetry was born. Born, not really, but this is where it was born for our mission. So at this point, we're 12 years into the idea. And then even though there's no mission yet, in early 2014, the first PACE science team was formed. And Lorraine was deputy of that one, just like she is for our current one now. Worked with headquarters to try to create an environment where oceans and atmospheres worked really, really well together. I think you did a fantastic job with that. And this is an EOS article they wrote with the lead at the time, Emmanuel Boss, about how this mission might proceed scientifically if it were to really become a thing. So at this point, we're 14 years into the idea. We have a science team, but we still don't have a mission. Okay, late December 2014, a letter of direction comes from headquarters. This basically means at this time, headquarters has decided that PACE is a real thing. And they were going to invest the money required to actually build this mission up around it. There was much rejoicing, and formulation of the project started in, let's see, January, February of 2015, and that's really when the fun begins. Brian and I started our roles as project scientists, February of 2015, I think. I've been at it for a little while. So I mentioned, okay, sorry, what you can't see in here is that it is really talking about OCI. They designated the mission So it's not a competed mission. And that actually had some turmoil in the community too, because there were rumors floating around that this would be competed, meaning centers, universities could all compete for this. And then out of the blue, NASA says, nope, we're going to give it to Goddard. And Goddard's also going to build the Ocean Color instrument. And a lot of that is for good reasons, because all those studies I showed you before actually showed that there were credible designs being percolated. Polarimetry, however, if you read the fine print, is a secondary instrument and not required in the strictest language of the law. So they want a secondary polarimeter instrument, but then they say there's going to be an acquisition strategy meeting that decides if we can afford polarimetry on that. And so what that is basically saying is you could go ahead with no perimeter, but you better not. You can give it to JPL, which is a perfectly legitimate option, or you can compete it out in the community, but as long as Goddard doesn't get it because they already have an instrument. And then let's see what it says. Okay, so this is where I need my notes. So this became the, this is still 2015. Polarimetry, everybody wants, but it's not really part of the mission yet. This is where Brian and Lorraine and others were really critical. If I remember this right, Brian, like November 2015, you and Otto Hasenkamp were at a meeting in the Netherlands where you started talking about the idea of Specs 1, and Otto's the PI for Specs 1. We put a request for information out on the street in the summer of 2016, and this is the time when JPL and industry can all start making their pitches for whether or not they can contribute this. Meanwhile, and I haven't told you this, PACE is what's called a design to cost mission, which means we got a number, and a number that cannot under any circumstances be exceeded. And so we only know we can afford about this much for the polarimeter. Those RFIs came back and they were too expensive, frankly. So by middle of 2017, it was a really dark time where we didn't think there was going to be polarimetry at all. When you just rack up the cost of a launch vehicle and the spacecraft and an expensive OCI and the fact that you want to be able to fund science teams and all of these things, you know, we were talking tens of millions of dollars for polarimetry, not hundreds. And if you want the Cadillac, you know, big OCI type, huge, does everything, it's expensive. Sometime during that year, we were at UMBC. And I remember having lunch, and Vanderlei Martin, who is Lorraine's PI on HARP2, was sitting next to me so frustrated because of this. And he turns and he goes, what if I just give you a polarimeter? I'm like, yeah, you're cute. So sure. He's like, no, think about it. I'm like, all right. So I went back and told Brian and told the project manager at the time. Vanderlei said he's going to give us a polarimeter. He was like, oh. And took the bait. And Brian did the same thing and started talking to the consortium of organizations in the Netherlands. And somehow the stars aligned. And even though they're not free in the truest sense of the word, because they're contributed instruments, this worked out, which is a surprise to all of us, but really, really, really spectacular. And what you're going to learn is that these two polarimeters in combination are badass. You know, they're not the big single one you might have envisioned going in, but they're going to be great. Okay, so with all that, and throwing up an eye chart for an organizational chart, but the project is formed. So at this point now, the organization that's going to build the mission has been formed. And I brought this up because I want you to know how big these things get, which drives cost, but also to show you some names that you're going to meet tomorrow and over the course of the mission, over the week, I'm sorry. And so the big boss of any mission like this is the project manager. They are typically engineers, usually have some interest in science, but their entire reason for being is schedule and budget. They're the ones under the most pressure, which is you're doing for HARP2 in many ways now. So, they're the ones who report to headquarters. They're the ones who report to the highest ranking scientist at the agency. They're the ones who get yelled at constantly. But our role is to be their best friends because otherwise they're not going to listen to us. But you might meet Mark on the tour. So then a lateral to this is project science. And in this case, this is where we come in. We are in an independent reporting chain because we're the conscience of all of this. Brian is with me in the project science staff. Antonio Menino, awesome guy, couldn't be here, he's on vacation, but he is a major contributor to the content for all of this as well. Then you have all the project staff, and these are the folks you're going to meet. Gary Davis, who's the mission systems engineer, he is basically the person responsible for putting the entire thing together. He has to know more about everything than anybody else, because he's the one who's going to take all the little pieces, put them all together, and make sure that everything can talk together and works. You'd be shocked how much we have to invest in safety and mission assurance, and that'll be Brad. And he'll come in because everything we do has to be risk protected and space worthy, and it is amazing. You'll watch, I don't know if you'll see this on the tour on Wednesday, but if there are 10 people in the room bolting something on, 7 of them are SMA because they're talking about, okay, this bolt, this torque, do it now. Nope, step back, we're gonna practice. Crazy. Observatory manager Beth, she is the entity responsible for putting the entire spacecraft together. Her counterpart, Veronica Pinnick, the INT manager, is the busiest person in the building right now because her responsibility is making sure all the small parts get assembled into the big parts you see. So she's herding all of those cats. We'll meet our ground system manager, and you'll meet folks from OCI as well too. And Eric will be here tomorrow, and he will explain how OCI works. The important thing to know about these is that even though you see a lot of little boxes, each of these boxes has its own chart with like 40 other boxes too. I mean, there are probably 500 parts of people working on a mission of this size. And they come and go. They're not familiar with the mission. We don't know all of their names. In many cases, they don't know why they're building what they're building. They just love building. In our case, the science staff that we have love what they're doing. You're going to meet Aaron and at least Aaron, maybe not Natasha, on Wednesday. Brian Franz, who's our science data segment manager, was supposed to be here today, but he's not feeling well. And then if you look at the project science organization, you know, this is kind of how everything ebbs and flows in my group. You have the external science team, which is inclusive of Peng Wang, Rain, and that's 25 people, 25 projects and 100 people. You have program science. Okay, so these are the folks you're going to meet tonight, and we're really lucky that we're going to have 3 of the 4 on the list plus a bonus. And you don't know that, but we've already had a program scientist here all morning, Joel Scott sitting in the back. So I don't think Laura's in, oh, Laura's back there. Hey, Laura, you left the car. So, well, welcome. Laura is the program scientist for PACE. She is the headquarters counterpart to what I am. So we spend a lot of time talking to each other. I deal with the Goddard stuff, she deals with the headquarters stuff, and we do our best to get what we want from both sides. We have a communications team. I bring this up because you'll meet some of them on Wednesday. And then the people you really care about for the late week lectures are all of our project science leads. And so I just want to give you an introduction early to Fred Patch, who's going to come in and talk about all the hands-on data flow that you're going to be interested in. That'll be Thursday. You know Ivana already, but Amir and Andy will also be visiting to talk about the science applications. So anyway, this is just to give you a sense of the size of the organizations itself. All right, so the project moves forward, and now we get into the design studies, which we'll talk about a little bit more in the morning. But there's a lot of decisions that you have to make, especially with a fixed budget, because you can't just keep going back saying, I need a little bit more money, I need a little bit more money. There's also all of the reserves that you carry. Reserves are money that you leave for a really bad day, because something always goes wrong, and you just need a little pot of money on the side for that. We put these all into technical memo series that are online if you care about them, but I brought them here just to give you a sense of the kinds of things we were looking at early in the mission. Because you spend the first half of the mission in CAD, PowerPoint, and engineering design studies. You're not building anything. We only started building stuff last year or so. But we talked about OCI coverage loss from glint and tilt change, so we actually have mathematical formulations for what is our angle? How fast does the instrument have to tilt? Because you can't do it instantaneously. Design studies and altitude reduction. So we're flying at 676.5 kilometers, but there was an idea of trying to get a LiDAR to follow us, which would have been really damn cool. Problem is LiDAR use a lot of power and they do better when they're at a lower altitude. So they want to fly roughly 400, 415 kilometers. So there was a whole design study related to what if we flew pace lower, and it turns out it doesn't really work. And so we needed to do those kinds of things. Choosing the SWIR bands, yada, yada, yada. You can read all of this on your own. Just understand there's a lot of different tricks and things that had to go into this, and this took years. During which we were in the dark times where we were canceled by the White House 4 years in a row. So now there's a morale issue we're dealing with too. Because when you get canceled in the White House budget, you don't stop working because that's not the real budget that passes through Office of Management and Budget. It's just a recommendation from the White House. But yeah, we got canceled 4 times in a row, which is where the applications program and PACE really, really started to take root. We were reaching out to the Navy, and the Navy really likes light penetration. They really like particle sizes. They really want environmental characterization of land, ocean, and sea. So we got an endorsement from them. They are super keen on polarimetry. And then we started, really drilling in data applications and how this kind of mission benefits economy and society too. And those are just examples of brochures that we made. But think a lot about applications as you start making career decisions because they're becoming incredibly important. And it doesn't necessarily take you away from, fundamental research. It saved us, it really did, and there's so much interest, and you'll learn from Erin and Natasha how they're reaching out to tribal communities. They are dealing with all different kinds of air quality and water resource managers. There's a lot of energy for a mission like this. So as you proceed, don't forget about that. At the end of the day, hey, we have a mission. This is the glamour turntable of what the observatory looks like. You will see most of it on Wednesday, but still in like 2 or 3 different pieces. Zooming in just, sorry. You've seen this already before. But again, we have the ocean color instrument. I will point out that there are simulated data available if you ever wanted to play with that. We might do a little of that on Thursday. You have our small but mighty polarimeters. You'll learn a lot about them in the next 2 days. And so here's where we are. In boring NASA lingo, we have phases, mission phases. So pre-phase A is when they give you the mission, but you have to spend all of your time on paper deciding what the mission actually is going to look like. And then you go to a major gate review and you get a new agreement with headquarters and you move into phase A. Phase A are design studies. That's where all of those headaches coming up with how should this look, what should we build, should the instruments do this, should they do that, whatever. Phase B is now when you get preliminary designs for all of the elements. How does the ground system operate? Actually have a credible design for it. And then you go through a crap ton of reviews with independent experts saying, that's not gonna work, that's gonna work, over and over and over. But this is the gate where you just have to tell them on paper, you know what you're doing. We're in the middle of phase C. We're actually at the end of it. Phase C has been really, really fun with the exception of getting shut down for COVID. But it's fun because you're building stuff and you're testing stuff and you get to go watch things in thermal vacuum. But at this point, when you're in phase C, you have to go through all your critical design reviews. At that point, you've kind of dabbled in building things so that you can do some fundamental testing. You have to get to a system integration review, which we will have in the coming months. But the reality is that the engineering test units, the practice units have all been built and characterized, and all of our flight units are built. So we're actually timed to this. I know I said I've been thinking about this a while, but we were timing this class so that we could actually go and see real hardware, just not fake versions of it. And that's why you'll see the real OCI sitting on top of the real tilt system and the real spacecraft with Specs 1 bolted onto it. And you'll see HARP, is HARP here or is it Goddard? HARP here, Thursday. Beautiful. You'll see all the parts. They're just not all together yet. Then in phase D, you finish putting everything together and you launch. Okay, so science community engagement, just so you are aware of the world around you. We have a science team, the second one that was competed in June of 2020. It's in its second of 3 years. There will be a third science team competed next year sometime. We have 2 system vicarious calibration teams. We'll talk about what that means later, but these are instrument teams that provide the ground reference data for calibration once the instruments are on orbit. We'll have validations team, and you'll learn a lot about our applications program as well. A little bit about the science and application team, just to give you a sense of the size of it. 24 teams, more than 100 people, some international partners. Their purpose really is to be coming up with the next generation algorithms and approaches and data products. Like right now we know, with some exceptions, like what Lorraine was just saying, that for our heritage, algorithms can be applied to OCI when you have the right wavelengths there. But the polarimetry and the hyperspectral analyses and the spectral derivatives and all of these other things are still in their infancy, in the sense they haven't been applied to orbit. And so the science team has been very busy doing that. We have an early adopters program. So this was, again, and these are places where you can get involved. The early adopters program was part of our mandate to create an applications program. And right now we're at something like 25 or 26 different projects around the world that basically stay involved with our applications coordinators. It's voluntary, but nevertheless, they say they find the meetings useful, and we pair them up with science and application team members so that there is a connection to the full science team. Hopefully you visited our website at this point, but I just wanted to give you the home of the technical memos that exist in case you want to do some background reading. If you are interested in the deep dive into every data product, you won't get this on Wednesday. There's just not enough time, but that information's put there. It will be where everything lands for spectral characterizations and all of our simulated and so forth. Number of papers out there, no ego intended, just if you don't like my history lesson, you want a proper one, that's where you go for it. And then going back to the dark times, and then eventually reiterating something Lorraine said, just when you're building these kinds of things, you just have to persevere. You're gonna get knocked down 1,000 times. So if you're a Star Trek fan, this is how we persevered through the early part of the previous administration when Space Force was really popular. It's like, well, what can we do to this mission to protect it? And then we thought Space Force, Klingons. And then things like COVID hit, but there are still so many ways that you can collaborate with each other, find them. This is the weirdest one I dealt with. But headquarters and Goddard got into a little baking battle early in COVID, and then our ESA colleagues got involved, and we just collaborated through sharing pictures of stupid things we baked. This is a galette that I made that acknowledged that ESA and NASA were working together on something that looks a little bit like CWIFs. So figure it out. You guys got it. Okay, cool. So I'm done. Any questions on that long history? Yeah. That was sometime in the middle of 2015 when we got a mandate to change the name, to get rid of the pre. And we iterated for months and then decided to change one word and remove the and. There used to be and ocean ecosystem, and now the and is officially gone. So when you pay taxes, you remember that. Oh gosh, this probably shouldn't be shared, but we went through a long internal survey about changing OCI to something else too, because Ocean Color Instrument really doesn't describe in any way what this whole thing is all about, and it's not super clever. The votes were in, and the name stayed the same. So anyway, any other questions? Oh, right. We are launching on a previously owned Falcon 9 so SpaceX is launching for us, out of Kennedy Space Center at Cape Canaveral, Florida. So I went through that too fast, I'm sorry. Oh, right. Let me do this again. Okay. So you have to make some choices that are associated with risk and instrument duration and redundancies. So there is a mission classification, ABC, doesn't matter. We are a Class C mission. A weather satellite would be a Class A situation, and basically a Class A. The designation is how critical is this to the nation for the investment? So you have the military and the weather satellites that are Class A. Like, there's a national security issue if something goes wrong with them. And that translates into more money for more redundancy. So if something breaks, there's a backup. And even more so, like with the satellites that VIIRS flies on, which are used, it's called the JPSS program, as well as the GOES program, which are the weather satellites. They're so redundant that they fly two at a time, they launch a third, get it up and running, turn off one, but don't decommission it in case one of those goes bad, and then they can turn it back on. So huge levels of redundancies. And as you go down into like a do no harm instrument, which unfortunately our polarimeters are, there's no redundancies. If it breaks, it breaks. We're in the middle. So to answer your question, the design that we could afford is for 3 years. What that is an engineering number to say that all of the risk assessment that goes into building the observatory can ensure 3 years of design life, but typically we have 10 years of fuel. So, and MODIS, which is I think Class B, was built at Goddard and, oh God, 22, 23 years old now. So, I mean, still chugging away. So we're being optimistic that the design life versus the actual life are not coupled. And it would be, in my personal view, it would be an absolute failure if this was a 3-year, 4-year mission. I mean, we need a decade plus for climate science. Yeah. Speaking only for myself. Yeah.
During the design of the mission, do you interact with other teams from the forthcoming mission, like SCOPE or NBG?
Yes. It is not as integrated as you might want it to be. And it depends on where the mission is being built. That sometimes it's easier to communicate with missions being built with at the same center than it is to be built elsewhere. It also depends on varying requirements that they might have versus what we have, but we actually have a series of working groups designed to, have a monthly tag up with the aquatic community for SBG, a similar one for the terrestrial community, maybe someday an atmosphere one. But yes, you would want to do that.
Is there a plan or some example how space interface with other systems in the system? So let's say ESA or
I'm having trouble hearing you, Lynn, I'm sorry.
how does space interface with the other centers, so like ESA or like government?
Oh, with the data streams?
Yeah.
I love that question. Well, the first layer of that is everything that NASA produces is within its data latency, publicly available online. So in our case, we have a requirement to have data on the street within 24 hours, but it's going to be 3 to 6 hours on average. And ESA and others are moving towards that model as well too. So in terms of data sharing, it's becoming a lot easier. In terms of coordination, in terms of, like if you wanted to have integrated algorithms or merge data products, it's not ad hoc per se in my view, but it is somewhat in its infancy. I mean, you have the IOCCG and these coordinating groups, at least, and I'm speaking for oceans here, where there are substantial attempts made to synergize these things. Sometimes politics gets in the way of that, so a lot of it is done more with individual researchers who are partnering to do these kinds of things. I mean, Laura, do you want to add anything to this? I think you'll see some more of this too, probably when Arlindo De Silva talks. He's our Earth System modeler, will be here on Thursday morning. And you see a little bit more of this integration of products at that modeling level, where they're more agnostic to anything in particular, whose product is which, and more trying to assimilate different versions of data into a bigger picture.
There's also quite a few informal projects like do that the industry wheel and developed an algorithm that's going to be used on ESAs and EMSATs all over. We have specialists in the Netherlands, and they have their own algorithm. And so we have a project where we're comparing those algorithms to try and understand how the products that we get up space will match up or not with the products that come up pre-MI from EMSAT.
So the products or phase will be available like right after launch of the satellite, or is there a period of
So it will launch, and then there's a 60-day in-orbit commissioning, and that is where things get turned on and tested. But launch plus 60 days, in principle, is when the pipeline should open. The one caveat to that is we will likely have the ability to process all of the advanced algorithms, but we may not be producing them right away. And the reason for that is, and again, going to oceans on this, is everything is based on a water-leaving radiance of some sort. So putting out a global map of phytoplankton community structure on the first day without having evaluated the radiances doesn't, to me, make as much sense as kind of staggering. You know, the code would be there if somebody wanted to do it on their own, but our endorsement of it would probably be staggered, you know, till there was some vetting of the products that lead, the earlier products that lead up to the more advanced products.
so the more advanced products? How long do you think?
Well, honestly, it depends on the science team and people in the room. We have a process now where we're actively integrating new ideas into our processing system. That takes some time. And with the simulated data, you can do some of the evaluation of all of this, but not everything. So those PIs who are out in the community that are actively working with us, those products will be out as soon as they bless them, really. So I don't think we're talking about 6 months or years, but you know, it might be a month of evaluating the radiometry and then saying, okay, I think this is good enough, we'll put a label on it, kind of thing. But we're kind of learning this as we go too, because it's, as we'll talk about later in the week, validating hyperspectral information, validating multi-angle, I mean, the volume of information you're going to get is unlike anything most of us have seen. And so there's so much to do, which is why we wanted to have that Friday session on performance assessments and uncertainties, because we're kind of learning with you how to do all of this.
I have a follow-up on that. So in this timeline, where does the validation cruises
I had a pointer and I didn't use it. Here. So we'll launch. So phase D runs from launch to that 60-day checkout, and that PACE validation science team we're forming will focus on this year in coordination, potentially with an aircraft campaign, and then persist through at least the first 3 years of the mission. Anything else? Oh,
So are the validation sites already selected?
no. We know we will use AeroNet, and we know we will use AeroNet OC, which is the ocean color version of that. We will do the aircraft campaign in 2024 will be off the west coast of the U.S., off of California. But the remainder of the validation sites will be determined through a ROSES competition. As we speak, I'm working on it. That's what my other. Yeah.
Do you know what file sizes are going to look like?
File sizes. We're going to bring Fred in for that. They're not small.
Is it going to be like, can you download them on here? Is it going to be cloud accessible? Or?
So that's another interesting question. Pace over its lifetime will migrate to the cloud, but because this talk of going to the cloud for everybody happened after our design requirements, it'll start as a ground system. I don't see that being forever, to be honest. Things are moving at different time scales there. Acknowledging that, if you have 208 wavelengths, that file's pretty darn big. And that would be just for like remote sensing reflectances. And then you have files for aerosol products. And then you have files for inherent optical properties of the ocean, which don't have to be at 208 wavelengths, but you want to have some meaningful ones in there. And then we'll have other files with biogeochemistry and other files with clouds. We are working to identify subsets of these things. So there should be, for example, in water leaving radiance or remote sensing reflectance, you can get everything if you want it, but you could download a version that only has 36 wavelengths in it too to keep the file size down. We're also talking about, for like air and water quality, if there are 5 to 10 key parameters that are across different files, combining them into one. So let's say somebody with interest in that doesn't have to go and get all of the information as well too. And then some of the interesting ones is like we do all of this at what you'll learn is called level 2, which is in the satellite coordinate system, but the big global maps get processed from all those. Do you really need 208 remote sensing reflectances globally? The answer is probably not, but it depends on who you ask. There might be 10 people in the world who want it. There might be 100, I don't know. So.
Just kind of going back to the launch, I was just curious how the decision was made to go with the Falcon 9 for the launch vehicle.
Money. Yes. So there is an organization at NASA called the Launch Services Provider. And like most things, it's a competition, and then it goes to a source evaluation board. And so this all happened. They basically say this orbit, this duration, this time frame, and then SpaceX versus United Launch Services and other places will all bid for it. And then the source evaluation board decides who's going to win it. And the weird thing for us, but it's a really good thing, is it's very rare to have an Earth science mission launched from Kennedy. So we're one of the few to do it, but it's good for us because it's so much closer to Goddard. We're not transporting or doing anything cross country. Yeah.
On global representation of data coming from type, will there be particular focus on the Southern Ocean as well? Again, algorithms represent the Southern Ocean better than maybe.
Yeah. There's certainly a lot of interest in that. I'm trying to think if, I don't believe anybody on our science team right now is specifically focusing on the Southern Ocean, although I do know that one of the science team members has a side project with a bunch of floats in the SOCOM, I believe. So they're basing a lot of their work from information collected there. But you're touching on a really interesting point. Like the NASA mandate is to get global data products out on the street. And what we're not really good at is distributing regional data products. We always have the processing tools for it available if an algorithm exists, so you could do it on your own. But if there was a really robust Southern Ocean algorithm that maybe didn't work anywhere else, you could talk about routinely producing that data product. And that's one of the ongoing conversations, one of the things we need to figure out, because we don't do that right now. All right, if you can think of anything else, around a week, almost full time. Let's see, I forgot to mention earlier that the presentations will all go online and they're all being recorded. So as we're getting into the more computationally intensive presentations over the next couple of days, don't stress out. You can always go back to the material. So I think lunch, they open at 11:30, so we can start our break. All right, cool. So let's meet back here at 1 o'clock.